states in vortex core as well.
Okay. Thank you, Chairman. And good evening. It's a real pleasure to be here at this meeting in such an exotic place, at least for me. And so I thank the organizers for the kind invitation. The work I'm going to present has been largely motivated by this recent experiment done on YBCO by Jens Breuer, Ivan in the group of Christoph Renner, and also by interactions with Herman and his collaborators about the tilted vortices in niobium diselenide. As you all know, and as this workshop demonstrates, there are different ways to look at vortices. And for this talk, I will take the point of view of local spectroscopy. So this is the point of view of scanning tunneling spectroscopy. And I will show a method to solve the Bogoliubov-de Gennes equations in order to access the electronic structure in the vortex cores. So the quantity of interest in this talk will be the local density of states in and around the vortices. And I will be mostly interested in the quantum regime and in the clean limit. So the materials I have in mind are cuprates, which are very clean and have very short coherence lengths, but also materials like niobium diselenide, which have a longer coherence length, but are still quite clean. So, what I want to explain is a method to solve the Bogoliubov-de Gennes equations in situations where the other methods are in trouble, and more specifically, the other methods are efficient in treating an isolated vortex, as there have been many examples in the past, or ideal vortex lattice at relatively high field in such a way that the unit cell of the vortex lattice is sufficiently small and you can use the Bloch theorem with appropriate boundary condition and solve it. But we may wonder how useful is that in the end, because at least to my knowledge, no one has ever published the spectrum of an isolated vortex. So this isolated vortex problem is more of academic than practical interest right now. And also with the techniques that are available right now, the fields at which these calculations are done are quite high. Typically for cuprate parameters, these are 10 to 30 Tesla fields, and in practice, most experiments are done around 5 Tesla. Last but not least, the vortices as they appear in STM experiments are often disordered. Little bit disordered or very strongly disordered in such a way that talking about a vortex lattice does not make much sense here. So this shows the need for a method to solve the Bogoliubov-de Gennes equation in situations where the vortices are disordered and also at very low field like here or at very high field. Okay. We have seen, by the way, other examples of this disordered vortex lattice in the talk of Isabel yesterday. So let me specify the problem a bit more. What I want to do is to solve the Bogoliubov-de Gennes equations. They are written here compactly, and I want to solve them in real space because I want to calculate the local density of states. So this is the Bogoliubov Hamiltonian, de Gennes Hamiltonian. It has kinetic energy terms on the diagonal and these pairing terms of diagonal, which, as you all know, are set by the self-consistency conditions. And since by habit I prefer to think in terms of Green's function, I will immediately introduce the Green's function, which for this type of mean field theory is simply the inverse of the Hamiltonian with retarded energy. And we want to evaluate this in real space representation because this is directly connected with the quantity we are interested in, and which is the local density of states. Okay, so this is the setup. And already there you can see why the conventional methods are limited. Because if you take a system of n by n sites, for example, in a 2D problem, the size of the Hamiltonian will be 2n squared by 2n squared. So if you have 100 by 100 sites, this makes 10,000 sites. You have 20,000 by 20,000. This is your Hamiltonian. And therefore, if you want to diagonalize the Hamiltonian like this, or if you want to invert it like that, what will be the bottleneck is the size of the Hamiltonian you can fit in your memory and diagonalize. Okay. We have seen an example on Monday by Yuki Nagai, I think, of a calculation of this kind, where the largest system which could be considered was 144 by 144. So you see that with this 100 by 100, we are close to the maximum we can do. But in fact, this is not terribly large. For some problems, 100 by 100 is enough, and you can do what you want to do. But for other problems, it can be too small. So this is typically the case of niobium diselenide, which has a lattice parameter of 3.5 angstrom, a coherence length of 10 nanometers, and therefore a vortex core in that system already contains 60 lattice parameters, and therefore if you have only 100 by 100, it's not possible to make this calculation because the other parameter will not reach the asymptotic value before you reach the boundary. Okay, so this is clearly too small. So the method I'm going to describe is able to do 1,000 by 1,000, and this is a 2 order of magnitude improvement. So how is this possible? It is possible thanks to an expansion, which is known since quite a long time, but it was first applied to Bogoliubov-Desen equation, to my knowledge, by François Peters, here maybe in the audience, and his collaborators. It's a little bit like a Taylor expansion of this inverse Hamiltonian, except that instead of simple polynomials, we use Chebyshev polynomials. I don't want to discuss all the details, not so important, but I just want to make 2 points. The first is that in order to calculate the Green's function in real space, we need these matrix elements, which are obtained by applying a polynomial, Chebyshev polynomial of the Hamiltonian on the state vector, which represents electron localized at point R. This is just, a very simple vector having zeros everywhere and a 1 at the position corresponding to this. So the first polynomials are trivial. T0 is the identity, T1 is a Hamiltonian, and the next one can be obtained by a recursive scheme because the Chebyshev polynomials obey this recursing relation. So you see that the only thing you need to do to implement this algorithm is to be able to calculate h psi for an arbitrary vector psi. And this is what saves us, because in order to compute h psi, you don't need to store h in the memory. You can program the way the Hamiltonian acts on a vector. And this is the first key which gives access to very large systems. The second key is that the calculation of the local DOS at 2 different points are completely independent. You just start with 2 different vectors. So this algorithm scales ideally with the number of processors you have because you do it in real space. And this is the second interesting element. Okay, so there we have the first ingredient of this method I want to explain. It's a Chebyshev expansion of the Green's function in real space. It's memory inexpensive, can do very large systems, and of course you have an exactly similar expansion for the anomalous function, which can give you the self-consistent loop, and by which you get the order parameter. So, but now to start the calculation, you need an order parameter. You will say, okay, the order parameter is set by self-consistency, that's right, but I need to start the self-consistency with something. And this raises a problem when you have an infinite number of vortices, as I want now to explain. So to explain this, let me just take a single vortex first. This is the order parameter shape. It has some profile function which describes the core. It has some phase, which is just geometric angle. This is the top view where you see the modulus, and this is the phase which has the winding by 2 pi. And just for illustration, this is a typical local density of states ongoing from the core to outside. You have the zero bias peak and the gap outside. Okay. The model I use for these illustrations is not very essential for the discussion, but just for definiteness, it's a square lattice with D-wave pairing. So the D-wave pairing lives on these bonds with different signs. This is the microscopic scale, and here you see the widely different scales involved in the calculation. This is the scale of the Chebyshev expansion, which contains 1 million microscopic lattice units. And for comparison, I also show the scale of the vortex lattice in the illustrations I will give. Let's go back to our phase problem and go to 2 vortices. So for 2 vortices, I can just take the product of the 2 profiles for the modulus and the sum of the 2 phases for the phase. This is very close to the self-consistent solution. And this is the top view again. You see that in that case, the DOS is split because the overall vorticity is 2 rather than 1. But that's not what I want to discuss. I want to go to a vortex lattice. So let's build a finite vortex lattice like this. You see that because you need to have a branch cut discontinuity going from each vortex to infinity, the distribution of phase becomes more and more complicated as you go away from the center. This is 5 by 5, this is 11 by 11. And now the question is, does such a finite vortex lattice provides a good model for an infinite lattice if I want to compute the DOS in some of these vortices? And the answer is no. Let me illustrate this by a simple example. If I take this vortex in the middle, I calculate the local DOS. For the 11 by 11 lattice, I get the thin line. For 101 by 101, I get the thick line. It's the same. So this looks very good. I have a zero bias peak. It's very quickly converged in terms of size. And everything looks perfect. But I now just go to the next vortex. Now, everything is converged very quickly in terms of size, but the spectrum is totally different. And of course, in an infinite vortex lattice, these two are completely equivalent, and I should get the same spectrum in both. So what's happening here? What's happening is simply that we are summing geometric phases from all these vortices to determine the phase at one point, and all these contributions of order 1, and there is huge cancellation between them. So when I am in a symmetric situation, the cancellation works, and I get the correct spectrum. But when I am just slightly off-center, there is no cancellation, and I get something weird. So I can again illustrate this in a different way. Let me just go back to this 11 by 11, and now I am just adding a few vortex on the side here to break the symmetry. And you see, even though they are very far from here, the local DOS is already significantly changed. So we have to, in fact, take properly the limit of an infinite number of vortices, because we sum an infinite number of order 1 contributions, and these cancellations have to be done properly. So the solution we have used is described in this paper. It's simply based on making a unitary transformation of the Hamiltonian, which is similar to the singular gauge transformation introduced by Franz and Tesanovic a few time ago. So this is analogous to a gauge transformation, except that this gauge is singular. It has a delta function like peaks, singularities at each vortex center. But otherwise, it's just a unitary transform. And once you have done this unitary transformation, the final Hamiltonian has no longer any branch cut, and the infinite sum for an infinite vortex distribution can be done in a controlled way. So our gauge is asymmetric because it acts differently, as you see here, on the electron and hole part of the Hamiltonian. And this is more appropriate to treat disordered vortex lattice, while Franz and Tesanovic had a symmetric choice, which was good for periodic lattices. So this is just to show an example of what we are talking about. It's one of the vortex distribution we have, Ivan has shown just before. You see here the modulus. And now this is the function which represents the phase. After the gauge transformation, you see that each vortex is represented by a local perturbation of this function only. And that when this becomes periodic, this becomes also completely periodic, in contrast to the phase that we had before, which was very complicated. Okay. By the way, this is hyper-uniform with an exponent of 1.6. Now, we have the second ingredient of this method. It's asymmetric singular gauge transformation, which removes the branch cuts and allows to describe infinite number of vortices, ordered or disordered. So we can now take this and go to make some calculation with it. There are several illustrations in this paper. I will just flash two of them. And the first one is designed to address the following question. You may ask how far away two vortices have to be in such a way that they do not change the density of states in one another cores. Okay, how far do in S-wave superconductor the vortex states are localized within a coherence length, and you do not expect influence much beyond this limit. But in the D-wave superconductor, it's different, as I will show. So in order to study this, we take a square lattice with D-wave pairing as before, and we consider two types of vortex lattices with the same field, but oriented at 45 degrees or along the crystalline axis of the microscopic model. Then we solve self-consistently the order parameter, and then we calculate at the center of the vortex and at the symmetric point in between the vortices, the local dose, which is shown here. This is a relatively high field, and you see that in the cores there is hardly any peak, and in between there is hardly any gap, so the local dose is strongly perturbed by the presence of nearby vortices, and furthermore, it depends on the orientation. Although these are the same field, so the local dose in each vortex feels the orientation of the field relative to the microscopic lattice. This was already known since a calculation by Han and collaborators in 2002. So now what we can do, we can compare these two spectra for the two orientations, compute the correlations, or 1 minus the correlation between the two spectra to measure how different they are. And this is a measure of how strongly the vortices influence each other. If there is no influence, these two spectra should be the same. Okay, so then we can start to decrease the field. At each of these fields, we solve self-consistently the order parameter, and we calculate the local dose. You see that the zero bias peak appears in the core. You see that the gap develops in between the cores. And this blue region is the region you could access with traditional methods. So that's nearly the smallest field you can treat. With this method, we can continue, decrease the field, and then you start to see something. And this, what you see is that the difference between these two spectra decrease exponentially, and this defines a new length scale, which is 40 times the lattice parameter, roughly. This has nothing to do with the coherence length. Coherence length is basically 1. So here you see a new emerging scale, which tells you how far the vortices talk to each other in a D-wave superconductor, and this is a very long distance. It has to do with the fact that each vortex at zero energy is degenerate with all the nodal excitations in the system, and therefore there is possible communication. So an interpretation of this length is given in the paper. I don't want to spend too much time on that. Okay, so now I will this was ordered vortex lattice, so it was just to show that we can go to very low fields and do the self-consistent calculation. That's advantage of this new method. Now let me just flash a few disordered vortex lattice results. This is a disordered vortex configuration in the same model as before. This is the zero bias conductance or zero bias density of state map. You see the vortices there, and next to each one you see the spectrum at the center. It looks, they are all a little bit different, and you see even one here which happens to be split, because these two vortices are quite nearby. And when we zoom for these two, we notice something interesting, namely that the actual center of the vortex here is this cross, and the maximum of the local density of states is not at the same place. So you have a distortion of the currents around these vortices because they are not symmetrically arranged, and this current polarizes the local density of states, and then you see a dissociation of the mathematical center of the vortex and the maximum of the local dose. And now if you go there at the point of the maximum and look at the density of states, it's not split. Okay. No, it's this one. And this here, this graph shows the currents distribution and the forces, which tend, of course, to put the vortices back in the equilibrium position. This is a zero bias conductance map, but the method has the advantage that it's an expansion in energy, so you can, once you have calculated the Chebyshev coefficients, you can compute at any energy without additional cost. So we can look at other energies, and here you see nicely the quasi-particle interference, but there is no impurity in the calculation. This is not interference on impurities, it's interference on vortices. Scattering of quasi-particle by vortices. You can then follow this as a function of energy if you wish. Okay, in the few remaining minutes, I would like to shortly describe the calculation which has been done to interpret the YBCO data, as Ivan has explained. Our motivation was this recent observation that the low energy peaks seen in YBCO have nothing to do with vortices. They are present in zero field and they do not change when you enter the vortex. So in one side, it's disappointing because a lot of theoretical effort has been put into building models which would produce these two peaks in the vortices. And myself, I have tried to do that for some time. But on the other hand, it's a new opportunity to go back and look into these vortices and try to identify what is really the signature of these vortices once you have removed this incoherent or parallel channel, whatever the origin of it, as Ivan has explained. So the question then is, what would be the BCS prediction for such a distribution of vortices as you see in the experiment? We can do this because now we have a model, we have a technique to treat large system, we have a model for the band structure of RBCO, and then we can extract the position of vortices in the experiment. We can embed this in a distribution of vortices which we generate more or less randomly. Some constraints are imposed. And then we can go on and calculate the local dose. And this calculation has shown a number of interesting things. First of all, you should not compare the calculation of an isolated vortex with a measurement done at 6 Tesla. These are very different. It's not qualitatively different, but quantitatively it can change quite a bit. So we need to take into account the vortices. Second very important point is that whether the vortex lattice tends to align along the crystal axis or along the diagonal has a huge role. This will strongly influence, even qualitatively this time, the vortex core spectra. And finally, what we have seen is that you also need to imagine where the vortices outside the field of view may be, because this information is needed to reproduce correctly the local density of states. So after doing that, we got this prediction, which Ivan has shown, so I will not insist so much. Just let me mention or draw your attention to the scale here. So this, what you have here is a fully microscopic calculation on 100 by 100 nanometer square, and this is clearly much beyond what has been possible until now. All right. So there is a new powerful method on the market, which combines Chebyshev expansion of the Green's function in real space and asymmetric singular gauge transformation, and is therefore ideally suited to treat two-dimensional lattice models in the quantum regime, in particular models of the cuprates, and this with arbitrary distribution of vortices, ordered or disordered at any field. So this method, in fact, pushes quite a bit the limits of what is now possible to do in order to try and simulate realistically STM experiments. And with this, I thank you for your attention.
Thank you, Christophe.